Okay, let's do a kinematics puzzle. And in doing this, let's learn how to think through the physics and the problem solving mentality that will help us solve puzzles that are different than this on an exam or even at the end of the semester on the final, and even as you go on further to other physics classes and upper division. Now, I like to do problems in class, so I don't like to post too many problems. There is a tendency, all of us, I suppose, for wanting the security blanket. How do I do this problem? Well, that really doesn't help. Let's think through a puzzle. Here we go. Take a look at this puzzle. We're going to look at number 81. And if you look at this, it says that the figure is this one, not this one. Now, that's a pretty good puzzle right there, too. So we're going to do this puzzle. Now, what I'd like you to do is pause and start laying out puzzle number 81. Now, as you do that on the paper, let me just say, it's really good. Part of what we're learning are professional skills. So I'm going to go, let's see, that's chapter 4, puzzle or problem 81. I want to put a box. I go, okay, I know what I'm working on, and everybody else knows what I'm working on. Boom. There it is. So pause and set that problem up. Go back, rewind, reread, and see what you've done. All right. So now I'm going to do that. I hope you've done that. Again, just watching is a very weak approach to learning, and you know, sometimes we kind of don't like the discomfort of the struggle, but the struggle is where you learn. Really spending the time and pushing through the puzzle until you've got it. So I've got this puzzle, and I'm going to do my standard physics problem solving. I'm going to do a quick read through of the problem. I'm going to talk about some physics that you probably wouldn't sit there and talk about. Have you noticed some things? And then I'm going to visualize and sketch it and gather and sort the data. You know what we're going to do. So let's talk about this real quickly. I've got an archer standing on a 15-degree slope, shoots an arrow 20 degrees above the horizontal. I know you can read this, but notice this. First off, it's 15 degrees and 20 degrees. Now, strictly, that would be one significant figure. This would be two significant figures. To get a tenth of a degree, boy, you're going to have some pretty good precision, and there are situations where you could, but so that might be reasonable too. But this is kind of loose, and you'll see later here it's pretty loose too. Anyway, above the horizontal, so I'm going to do that as shown in this sketch. How far down the slope does the arrow hit if it was shot at a speed of 50 meters per second from 1.75 meters above the ground? Now, again, how many sig figs? 3. How many sig figs? 1, technically. Now, that 0 could be a sig fig, but you might want to write that as 5.0 times 10 if you really wanted to emphasize 2 sig figs. So this is written rather sloppy. The picture's done for us, and that didn't have to happen, but we did. And what have we got here? We've got a 15-degree slope here. We've got the 20-degree slope here. Let's go ahead and go through this and lay the puzzle out. It isn't about trying to solve or get the answer. No one cares about the answer to this problem. You can probably look it up in the back of the book, but no one cares. What we want is how do we solve this. Okay, let's go about this. So I'm going to redraw this, and I'm going to visualize and sketch, and that means that on my sketch I need to make sure that I show visualize and sketch. I'm going to show key instance or states. I'm going to show my coordinate choice, and I'm going to show my variables and label them well because it's going to pay off for me. Also, I'm going to gather and sort my data. So let's see, where do I want to do that? Maybe I'll do that off to the side. It doesn't matter. Let's see how this comes out. So I've got G meaning given. What's straight up given? And I've got implied information, implied in the wording, and then I've got some methods that get me to what I want. Okay, and this is the methods. Okay. All right. So let's see what I've got. And the objective here isn't for me to do a very nice, pretty sketch. I could have done that on the board. But think it through as you would. All right, we've got an archer. Now, let's see. I've got this. Let's draw this reasonable sketch, maybe big enough so that I can see. I might use a protractor. I recommend that. Go like this. Here I go. 15 degrees is not very big. Don't draw 45 unless you mean it. But I'm not going to sweat it too much, and I'm just going to go like that. Okay. Now that's the angle of the surface, right? 15 degrees, no biggie. And I'm just going to sort out what do I know, what do I know. And they've drawn it so that it kind of lands, well, it lands here. Now I've got another issue with this problem. We're shooting an arrow. Is air resistance negligible? I mean, the feathers on the back are for a reason. And so I'm not very keen on this being a free flight, or if you will, free fall problem where the air resistance is negligible. However, we know that we can't deal with the lift that we might get on an arrow. So we're going to go ahead and treat that as a free flight. Now, this gets a little tricky, remember? An archer standing on a 15-degree slope shoots an arrow 20 degrees above the horizontal as shown. How far down the slope does the arrow hit if it's shot with a speed of 15 meters per second from 1.5 meters above the ground? And that's a pretty reasonable height above the ground. So I've got to look at that picture. And I've got to label where all that is. Again, pause and do that. So I've got to draw that somehow and show that this happened. And I'm going to draw it as a ball because an arrow is just kind of too much information and silly. So I'm going to go like this. And that's my ball. This right here, I'm going to put that information. If I don't put the puzzle pieces out, I'm in trouble. So this here is going to be 1.75 meters. Now this doesn't matter what order you do this. I just need to make sure that I get that. Now I'm going to go 20 degrees. Again, a shallow angle. So something like this. And they said, again, that the speed was 50 meters per second. So I'm going to label that carefully as my speed without an arrow on top of 50 meters per second. And I'm going to just double check myself because my head's going to be looking all over for my puzzle pieces. V1 is 50 meters per second. Again, sloppy. I'd want to see maybe 50.0 or something on sig figs, but that's fine. Okay, and I've got, again, a 20-degree angle. Now, I might label that, and people in textbooks often don't, but I'm going to label that as theta 1. You can see it's from the horizontal, but theta 1 is 20 degrees, again, unknowingly 1 sig fig. It's because there's going to be different angles. And so go ahead and subscript your angle. That's your speed, not your velocity, right? I have no direction there. This is the angle at that moment. All right, cool. So what's going on? Well, I want to point out a few things. Let's think about this physics. This is called the line of projection or the line of sight. That is not the path, okay? So you know what that is, line of projection or line of sight, you might write it down. Now the path, of course, is it won't go like this, it will curve like this. And again, I'm going to make the interpretation of the purpose of the problem as a study of free fall or free flight, as I like to say, meaning negligible air resistance, no other forces, no rockets. What do I know? Well, I know it's going to land here. Okay, so it's going to land here at some point, And I'm going to draw that state. Remember, these are key states. Now, we might want to do an intermediate state. So it's going to start diving down already and then come along here. That's the path, right? Which is approximately a parabola, actually an ellipse around the center of Earth, but we won't get into that. And okay, that's the path. That's the line of projection. Now I'm going slower than we would, but I just want to point things out and milk this for all it's worth. This is horizontal. Fine, there's my surface. Now, if I wanted to find out the peak, I'm going to go ahead and put that in there. That might be of interest. At that peak, this is state 2. And while they don't ask for it, I'm going to go ahead and do that. And what's going on at the peak for a projectile? Again, free flight. Well, it stopped vertically, right? It's going up, 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 and then down, 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 down. So there's no, I know at state 2, and this is implied information. That means that the way I've drawn it, V2y is 0. V2x equals V2 equals Vx at any time, because Ax is 0. Well, this is a good time for me to throw in my coordinate system. But let me label again my variables. Now, I should have a red pen, but I don't right here. I like to use a dashed line. That velocity is going some this direction. It's got these components. Oops, what did I do? I've assumed my coordinates without showing them. I know it's easy and perhaps it's obvious, but remember, you're going to have a lot of puzzle pieces as you get into more difficult problems. So I'm going to lay this down right over here. And since it goes up, I'll choose up to be positive. You can choose down to be positive if you want. But by doing that, I'm going to call this the y direction, or the plus y direction, where the arrow says plus. Next to it, I'm going to put ay is equal to negative g because it's free flight. I don't need that over my implied column. And then I know it's free flight. I'll call that plus x because it's certainly not going in any other direction. And what's ax? 0. It's neither speeding up nor slowing down in the horizontal direction. So I'll use vertically up and horizontally right as my coordinate system. Every vector can be broken up into horizontal and vertical. And so I'll do that. There we go. Now that's true too over here. So I'm going to call this state 3, even though in this problem we just need 1 and 2. I'm going to call that state 3. I'm labeling my states 1, 2, and 3. This is going to help me. It may seem slow. It's a much faster way to go about it to save you time, and you'll get good. I've got my coordinate choice clear. I've got my key states 1, 2, and 3. We could do any state, any instant. Remember, a state is an instant along that path. Once it hits, then it's no longer a projectile. While it's being shot, it's not a projectile. So we're looking at just after release to just before hitting. Now I'm going to draw this vector here. I know that there's some speed and some angle, and here's the horizontal. So I'm going to draw that angle theta 3 and V3. Okay, cool. Oh, what's theta 2? We don't necessarily need that, but it is there. Remember, we want time. We want displacement. We want velocity, speed and direction, broken into components. Displacement, in this case delta x and delta y, broken in components. And acceleration, which we know straight up. So, what do I say? Theta 2 is equal to 0. In other words, it's horizontal. So I just keep these notes so that I don't get lost and make a silly mistake. And what do I want here again? Let's go back to the problem. There we go. How far down the slope? Down the slope. Is that horizontal? Is that vertical? What is that? How far down the slope? I don't know. I need to go back. An archer standing on a 15-degree slope, got that. Shoots 20 degrees above the horizontal. Okay, hopefully I could draw that picture without them giving me the picture. How far down the slope will it hit if it's shot at that speed and that far above the ground? So I want to know down the slope. Now, this is going to be interesting. So I want to know from here to here, but not delta x. I want to know down the slope. So let me draw that as a question mark. How far? And I'm going to put an arrow because it's going this way. Don't put the arrow both ways like we do labeling lengths and widths and things like that. So that's what I want to know. Now, what else do I know kinematically about this? Again, we've got times, well, we got 1, 2, and 3. We've got displacements. So this arrow, for example, this state from 1 to 2, I've got displacement, delta x, delta y, delta x 1 to 2, delta y 1 to 2, if I wanted to work with it. Horizontal in my x direction, delta x 1 to 3, delta y 1 to 3. Since they're asking how far down the slope, I don't need that. I could do another problem. I'm going to clearly label this delta x 1 to 2. Once it's set up, you're nearly good. I just want to show where that displacement is. Got my times. I got my displacement. Oops, hello. Did you catch that? 1 to 3. Good to make a note. That's what will happen. Your head will be doing all these things. You'll make a mistake, and you go back and you check and you go, whoa, 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 whoa. And that's kind of the mentality here. Now, it does go up, but the delta y is the displacement. I start vertically here, and I end up vertically here. Delta y, 1 to 3. All right, cool. So I've got displacements. I've got velocities, and I know the acceleration. The velocity is always directed which way? Tangent to the path, right? Turn off gravity, it'll keep going that way. Turn off gravity, keep going that way. Okay, so this is the key. I mean, this is usually a hard problem for people, but it's really not if you break this all down. Now you might go, well, what am I going to do about that? The other problem-solving mentality, don't think too far ahead. We've been trained poorly. We've been trained to look for the answer instead of lay out the puzzle. So we are laying out the puzzle, and we'll see. I mean, if we don't get that and we get everything else, we've done a good deal of work. So let's move forward. So we want how far down the incline or the slope it lands. Just reinforcing that to myself. Now, I've got some information given. I've got this. I know that the acceleration's there, so I don't need to write that. What are my methods? So my methods are now going to come into play. As I said, we're assuming this is a free flight problem, that is an acceleration, as we've said. So that means a constant acceleration, and let's go ahead and do that. So let me see, what can I say? I want to make a little note here before we jump in, and I know that's maybe kind of annoying, but I just want to point out some notation here. I want to show you V1, speed is 50 meters per second. What about the vector? Well, you can write this a couple of ways. Polar form, 50 meters per second, 20 degrees up from horizontal. That's the amount and the direction. The amount for velocity is speed and direction. Now you can also write this, since I've chosen coordinates, which could have chosen coordinates along the slope. Believe me, that's probably not going to be easier because the acceleration would have components. Here we've chosen acceleration, so it's all 0 in one direction and all in the other direction. That's a nice choice. And what have I got? Well, so I'm going to have v1x. This is going to be relevant. I hat plus v1y j hat. Okay, and you're going to need that. That's the way we do this motion in 2 and 3D, is we divide and conquer. That's what vectors are all about. Now, how much is that? Hey, let me take a look here. I'm just exploring. I'm still laying out my puzzle pieces. So I've got a velocity of, I'm going to extend it, v1. I've got an angle of theta 1 relative to this horizontal. It's got components, which I draw as dashed lines, and I'm going to draw them at the tail. You can draw it here and here, as long as you've got the arrow, and the arrows go from the tail of the vector. Here's the object. It's not going anywhere. It's not there. It's just right there. It's moving, but in that instant, it isn't. In the instant, it's moving, but it hasn't traveled any distance. So I go from the tail of the velocity vector to the tip. So arrows on the components, arrows on the components, arrows on all vectors and all components, all components. This object is moving that way, which is partly horizontal and partly up. I know, it's a bit much, but we've got that. And we know that then I've got it as a positive V1, in this case, cosine theta 1 I hat. And then I've got it positive V1 sine theta 1 j hat. Okay, that's how much in the x, that's how much in the y. My equations are going to treat x separate and y separate and piece it together. All right, I hope you're clear on that. Now, if this angle is given, then it would be V1 sine of this angle. It doesn't matter which angle you use, you'll still get there. And then this would be V1 cosine, that's right. Okay, got it? So make sure that you can do that. And of course, this is this squared plus this squared square root, etc. This you can get from the inverse tangent. Let's get into it. Methods. What's our method of analysis here? Constant acceleration. You don't need to write this necessarily, but constant Excel. Great, we're taking a long time, but that's we're going to solve this. And when you do it, probably don't want to be talking through it. Here we go. So let's just draw this. I've got, I know my general equations. So it's two-dimensional constant acceleration with free flight. I'm going to apply it. I'm going to apply it 1 to 3 because they're asking about that. So I'm going to write this. This I'm kind of writing, but for your sake, but I will write this in my analysis so it's clear. And so in the x direction, horizontal x, I have the following. I know ax is equal to 0 because it's free flight. Therefore, I know that I have delta x 1 to 3 is vx delta t 1 to 3. Why didn't I subscript that? Because that's Vx at any time. That never changes. That's what that says. And the other equations just reinforce that. So I've got one equation there. Now I've got vertical. And I'm choosing that to be plus y. Since that plus y, ay is negative g. Don't put in the number yet. So vertical. And I'll call that, of course, the y direction. So just double, it's true that I'm, being redundant here, but that's how we catch mistakes, right? So I've got that up there. I don't need it. I can say this. Delta y, 1, 2, 3, since I'm using 1 to 3. If I did 1 to 2, I'd rewrite the equations. If I did 2 to 3, I'd rewrite the equations. That's equal to v earlier, 1y, delta t, 1 to 2. minus 1/2 g, because it's minus g is the acceleration. Delta t, 1, 2, look at that, 3, because the problem really only has 2 states, but I put in the third one. And there we go. All right, cool. So that's that. How are we doing? All right, so let's keep going. That's that for that. Now I've got V3 in the y direction. This is all only the y direction, right? Is equal to V1 in the y direction minus g is the acceleration, delta t 1 to 3. V3 y direction squared equals V1 y direction squared minus 2g, not delta t, but delta y 1 to 3. By subscripting like that, by laying out the puzzle clearly, everything's going to flow much faster. If you don't do that, you got problems. Okay, so I do have a red pen handy. As usual, let's see. And I've used up my red pen. Okay. Got another red pen. That's what happens. I actually use them up. Okay, now let me see what I've got. I don't have delta x 1 to 2. I do have vx, don't I? I could have calculated it up there, but and that would have been fine. But you see how you can plug in up here. 50 meters per second times the cosine of 20 degrees. 50 meters per second times the sine of 20 degrees. So I've got that. I don't know the time. I don't know delta x. Now I want to know how far it lands down there, but I'm not worried about that yet. I just want to see what my method's going to get me. I don't know delta y. I do know v1y. I don't know delta t. Of course I know g. So now I've got delta x, delta t, and delta y are my unknowns. I don't know I don't know the speed that it is hitting just before it hits. I do know this, I do know that. I don't know this, I do know this, I do know that. And I don't know that. Boy, what's going on here? What can I do? Well, I can do this. I know I can do this, so let me just not, again, get stuck. If you're going to go, how do I get there? How do I get there? Then you'll never get there, strangely. Okay, so what am I going to do here? Let's see what this all means. This is my method. It's got to work. I've got to simulate this state of confusion that is so frustrating. What do I do? What do I do? Well, you know this is what you're doing. Well, let's go back up here and see what we've left out. Oh, wait a minute. I need this. What is my delta x and delta? My delta x, let me draw it up here, is here. This is my delta x 1 to 3. That's kind of a triangle, right? Is that the distance along the path? No, not really, right? If you draw that straight line, that line is not the same length as that line. What do I know? What do I know? What do I know? How much down the path? You see where I'm going? Let me let you think about that. You can pause. How much down have I gone? What's the relationship here? What can I say? This is something you've known all along. This is problem solving. This is seeing physics. You know this. Okay, you know this. This is just basic math. Okay, that you know. What do you see? This is how much? Well, isn't it? What's that? That's my delta x1, isn't it? It's all still the same horizontal displacement. How much is this? How much is Just start looking. Just start, what do I know? What do I know? Oh, wait a minute. Look over here. Delta y 1 to 3 is from here to here, so maybe I should draw that over here and say, that's my delta x. Just start puzzling it. Here's my delta y 1 to 3, and that pen is going. Seems I've been doing a bit of grading. So here we go. Delta y 1 to 3, okay? So this is delta y 1 to 3 minus this, which I've written. Interesting. So the distance I want, my question mark, let me label that. I'm going to give it a letter because a question mark doesn't work. I'm going to call it D. Okay? So then what do I know? Well, I'm just going to write down what I know. D is equal to delta x 1 to 3 squared. It's a right triangle, isn't it? Delta x 1 to 3 squared plus delta y 1 to 3 minus 1.75 meters squared square root. So I know that. Cool. I know that to be true. Great. We good? So we're just writing out what we know. We're just right now I've got a puzzle. Now it's more of a math problem. The physics is here. The physics is laying out the puzzle. Coordinates, states, well-labeled variables and information, given, implied, want. Okay, I know I've got a method, so let me see where it takes me. Now I could go here and I could say, well, what are my unknowns? My delta t 1 to 3 is unknown, isn't it? Seems to be. My delta x 1 to 3 is an unknown. My delta y 1 to 3 is an unknown. My v3y is an unknown. 1, 2, 3, 4. Now I've got 1, 2, 3 equations. Why not 4? Because this is derived from these two. So I've only got 3 equations. I've got 4 unknowns. If I get these guys, I'm golden. But I've got 4 unknowns. So now I need another equation. Do I have to go back to state 2? No. Any earlier to any later state can be related directly as long as the acceleration remains constant from that earlier to that later state. So I clearly need, I can sit there and sit there and sit there and think about, oh, what do I do, what do I do? But I've identified that I've got, I don't know the time, I don't know horizontal, vertical displacement, and I don't know the y component of the velocity just before it hits. So I've got 4 unknowns, I've got 1, 2, 3 equations. This one's going to get me from those two, so I just need those guys. I need a 4th equation. So what else can I say? What's true? What other information have I not used? Let me go through. You see it? I'm going to use this for my velocity components. I'm not going to use this because we don't do it. I've got that angle I'm going to use that when I do it. I'm going to use that, I'm going to use that, I'm going to, hey, I haven't used that. That's the theta of the incline or the slope. I could call it theta S or theta slope or theta I for theta incline. I haven't used that. Somehow that's got to matter, right? If you're sloped at a different angle, it's going to land at a different place. That's physics. That is physics. Okay, and that is problem solving. And so you can relate that and you can go, oh, I know what's true. Is that this, which is delta x, and this, which now I'm just gonna, can I call that h? This part. Now that's not delta y, right? H is that delta y minus that. So from here to here is h. That's what this is. That's the h. All right, so what can I say? Oh, wait a minute. That's delta x over 1 to 3. That's h. That's d. Interesting. What do I know? I can relate this and this to this. So what's true? Let me see. Let's see. The tangent of 15 degrees, of 15 degrees is h over delta x 1 to 3. Now it's true, this is kind of a clunky notation, this delta x 1 to 3, but it sure keeps you straight, and that's going to pay off and teaches you the physics. Now I know that. How much is h? Well, it's this thing. Yuck. But I can still relate those things, right? I've got another equation that relates delta y, delta x. It relates two of my unknowns to a known value. So I got a fourth equation. 1, 2, 1, 2, 3, 4 equations, 4 unknowns. Once I've got delta x and delta y, I'm golden. I can get d that way, or you can do it however you want, right? So the rest is algebra. I'm not even going to do it. You can do it. You can play around, and that's math skills. Okay, you're not. It's important. It's a part of math, physics. Math is a part of physics, but the physics is seeing this and laying it out. The problem solving and the engineering, the stuff that we do in quantitative analysis and trying to lay things out, that's engineering. So this is really getting a good sense of how we lay things out and lay situations out. We draw them, and we say, what do we know? What's my method? I've got constant acceleration, but oh, doggone it, it doesn't give me enough. There's information I didn't use, so I can what can I say about that? The constant mantra is, what do I know? What do I know? I know this. This was given. I have not used this. What do I know about that? I could treat it as this over that. So I could say, hey, sine of 15 would be h over d. Cosine would be delta x 1 to 3 over d, right? So whatever you do, it doesn't, just write it out. Don't try to solve it before you've done it. So start tinkering around and play with it. Then you get out a nice new sheet of paper and you start playing around and mixing this up, okay, and doing the algebra, and you see where it goes. Now at this point, you might put in numbers, but it might not be that. I don't really care about V3 and I don't know. I don't really care about V3y, so maybe I'll just go with getting rid of that, since I wasn't asked. Maybe I'd be asked, at what angle does it land? Right? If I want to know the angle it lands, theta 3, I need V3x, which is Vx, because it doesn't change. I need V3y, and that angle would be V3y over V3x, inverse tangent. Take the absolute value, this over that. Inverse tangent is going to give me the angle that it's traveling just before it hits. Okay? So again, I just look into the problem, not into my head, not into a solutions manual. Is just killer. This is kind of a solutions manual, but hopefully I've talked through some of this and you follow it and you apply that struggle. It's a struggle. It's confusing. Of course, it's easier for me because I know the stuff. But if you keep looking, you keep struggling. When you solve a puzzle, there's a few things more rewarding than actually solving a puzzle like this. So I encourage you to play around, take new puzzles, and this is generally a puzzle that people find very difficult. And why do they find it difficult? Well, they get all confused, and so You got an equation, just give yourself plenty of room, make it clear, do the algebra. You know, you can state, hey, I've got these three equations, these three unknowns plus the fourth unknown, and I've got 1, 2, 3, 4 independent equations. I'm good. Since if I don't want that, I might as well leave that off. Now, 1, 2, 3 equations, 3 unknowns of use. Okay, I don't need t, but somehow I'm gonna have to get rid of it. There you go. I hope that helped. Cheers.